In this chapter, we will explain some fundamentals in order to understand some aspects of the physical layer. First, remember that the bit is in fact the binary information unit or binary digit is the smallest unit of information. In fact, the information transmission theory is the scientific study of the quantification, storage, and communication of digital information. The field was fundamentally established by the works of Nyquist and Claude Shannon. The field is at the intersection of probability theory, statistics, computer science, statistical mechanics, information engineering, and electrical engineering. It's what we call information theory. Digital signals. In digital communications, a digital signal is a continuous time physical signal alternating between a discrete number of waveforms that we call symbols, representing a bit stream. The shape of the waveform depends on the transmission scheme, which may be either a line coding scheme allowing baseband transmission or a digital modulation scheme allowing passband transmission over long wires or over a limited radio frequency band. A symbol is one of several voltage, frequency, phase changes of the digital signal. Baud rate refers to the number of symbol changes transmitted per second. A symbol may consist of one or more bits as determined by the modulation coding scheme. That is, in fact, the bit rate is higher or equal to baud rate. Remember that each symbol could consist of one bit or more than one bit. Return to zero and non-return to zero binary coding has two symbols, one for each bit 0 or 1, that represent voltage levels. In these cases, the baud or symbol rate is the same as the bit rate. Interferences and channel capacity. In communications, sources of interference are usually present and noise is frequently a significant problem. ICI, intersymbol interference, is usually caused by multipath propagation or the inherent linear or nonlinear frequency response of a communication channel, causing successive symbols to blur together. The presence of ISI in the system introduces errors in the decision at the receiver device. The effects of interference are typically minimized by filtering off interfering signals as much as possible and by using data redundancy, for instance, using checksum and CRC. Channel capacity, C, expressed in units of bits per second, is the tight upper bound on the rate at which information can be reliably transmitted over a communication channel. Another fundamental, the Fourier decomposition. Fourier decomposition is the way general functions may be represented or approximated by sums of sine waves and cosine waves. Pay attention that the lowest frequency cosine wave is a DC signal, continuous signal, DC component. Fourier decomposition is important for three reasons. A wide variety of signals are inherently created from superimposed sinusoids. Audio signals are a good example of this. Fourier decomposition provides a direct analysis of the information contained in these types of signals. Second, linear systems respond to sinusoid in a unique way. A sinusoidal input always results in a sinusoidal output. In fact, it's a linear system. In this approach, systems are characterized by how they change the amplitude and phase of sinusoids passing through them. Since an input signal can be decomposed into sinusoids, knowing how a system will react to sinusoids allows the output of the system to be found. And third, the Fourier decomposition is the basis for a broad and powerful area of mathematics called Fourier analysis, and even more advanced Laplace and Z transforms. Most cutting-edge DSP, digital signal processing algorithms, are based on some aspect of these techniques. Then, for instance, this waveform could be decomposed in that kind of sinusoid combination of sinusoid waveforms. The attenuation of a signal depends on the frequency. Higher the frequency, higher is the attenuation. The bandwidth of transmission medium is a physical property. The frequency range that is transmitted without large attenuation is called bandwidth. The bandwidth of the media, the bandwidth of a channel, the bandwidth of transmission media. The attenuation of signals, if this is the shape of the signal that is transmitted at the input of the channel, this will be the output, that is the signal that arrives at the other end. It suffers an attenuation and it suffers a deformation due to different impairments. Baud rate and transfer rate. Digital signals are transmitted at a constant step rate, also known as baud rate or symbol rate. The baud rate is the rate at which the signal changes on the line. The symbol changes. Remember, the symbol is a waveform, and the waveform change each time that the symbol change. For reconstruction, the signal must be sampled at the same step range or symbol rate or baud rate. 1 bit, that is a binary signal or binary information unit, or several bits can be transmitted per step. Then remember, if 1 bit is transmitted in each symbol, then the baud rate and the bit rate are the same. But if we could transmit several bits per step, we could transmit at a higher bit. The bit rate will be higher than the baud rate. The data transfer rate, that is C, the capacity of the channel, results from the step rate, RS, and the number of quantization levels. The number of quantization levels. For instance, if we had 8 quantization levels, then log 2 of 8 is 3. Then there is 3 bits per symbol. Then we could multiply the step rate or baud rate by 3, and we obtain the capacity of the channel or data transfer rate in bits per second, typically. Sampling theorem to Nyquist. Then Harry Nyquist established this principle. A signal filtered with bandwidth B can be transmitted by two per B samples per second, and if we respect this frequency, this sampling frequency, we could be fully we could reconstruct fully the original signal. If a signal consists of n stages, that is n symbols, n different symbols, the maximum data transfer rate is 2 per the bandwidth. Remember the bandwidth in hertz per log base 2 of n stages. If n is, for instance, 16, log 2 of 16 is 4. If b is, for instance, 1 megabit, then the capacity is 2 per 1 megabit per 4, that is 8 megabit per second. Channel capacity, then Claude Shannon discovered this property, that is the capacity which is the theoretical capacity of any channel. Applies only to band limited signals, that is band limited, that is the signal has a particular bandwidth. The information content of an undisturbed band limited analog signal with finite amplitude is infinitely large. It can be infinitely finely quantized. A noise always disturbs a signal, so no infinitely fine quantization is possible. We need to use a quantization that is the noise couldn't affect. For instance, that is the receiver could differentiate the symbols even if the noise is added to the signal. The signal to noise ratio from useful signal to noise signal is a decisive parameter for the information content of a signal. With all those principles, we could apply this equation proposed by Shannon. And then, according to Shannon, the channel capacity C can be used as a function of the bandwidth B and signal to noise ratio. Remember the signal to noise ratio, power of signal divided by the power of noise. Then typically this is the equation. If the signal to noise ratio is better at the same bandwidth of the channel has a higher could reach a higher capacity, information capacity, expressed in bits per second. The signal to noise ratio could be could be measured in dBs, in decibels, using the typical formula, that is signal to noise ratio in dBs is equal to 10 log logarithm in base 10 of the signal to noise ratio expressed in power. For instance, in that case, when, for instance, the signal to noise ratio in the base is equal to, for instance, if the power of the signal is 1000 higher to the noise power, then in fact the signal to noise rate in the base is 30 dBs. And this is typically the conversion of the Shannon equation expressed in signal to noise ratio in dBs. An example of data transfer and channel capacity. What is the data transfer rate according to the Nyquist theorem at the bandwidth of 2 MHz at 16 signal levels achievable? Then remember, 16 log in base 2 of 16 is 4. Then typically 2 per 2 megabits per log in base 2 of 16. That is a channel capacity of 16 megabits per second. What signal to noise ratio in dBs would be at least required according to Shannon at this bandwidth and the signal levels to carry out this data transfer? Then remember, this is the equation of the Shannon expressed in signal to noise ratio in dBs. Then we could deduce that in fact the signal to noise ratio in dBs is equal to 24 dBs. Remember, 30 dBs are it's a signal to noise ratio where the signal power is 1000 higher than the noise power. Well, signal to noise ratio of 24 dBs, it's approximately a factor of 250 times the signal power compared with the noise power. But the importance of those concepts is that if we would like to transmit higher information rates across a particular medium, for instance, twisted pair or a fiber, or an optic fiber, we could use some techniques in order to obtain a higher signal to noise ratios. And then if we obtain higher signal to noise ratios with the same media, with the same bandwidth, we reach higher capacity, channel capacity, then higher data transfer rates.